So Carnot heat engine. So it consists of four operations. So two are adiabatic process and two are isothermal process. Okay. So right now we'll see in detail. Construction we will see. So in order to explain this one, we require one piston cylinder arrangement, and it is insulated three sides, two sides as well as the front side, and this side also it is insulated. Only it is what we say, cylinder head is not insulated. Okay, means I can add the heat or I can extract the heat through this head. So for that reason I made it as not insulated. Now can you hear me now?
Yes, sir.
Yes, sir.
Okay, right. So one piston cylinder arrangement. Next we considered two walls. One is the adiabatic wall and second one is the diathermic wall. As the name implies that, suppose if I keep this adiabatic wall or adiabatic cover in contact with the cylinder, now the complete cylinder is insulated, even four sides. If I keep this one near the cylinder head, it will become insulated perfectly. Right, means this adiabatic cover will not allow the heat to enter into the system or to leave from the system. Okay, and if I keep this diathermic wall is a perfect conductor, whereas adiabatic wall is a perfect insulator. Okay, like diathermic wall is a perfect conductor. If I keep this diathermic wall in contact with the cylinder head, it will allow the heat to enter or leave the system. So it is the conductor, therefore it can transmit the heat through it, whereas it is an insulator, it will not allow any heat to enter or leave the system. Right, apart from that we have one source. As we know, source is a reservoir under high temperature and sink is the reservoir under low temperature. Okay, right, and here I have one working substance. Maybe we can assume as a perfect gas as the working substance we can assume. Okay, right. Now, so first initially the piston is nearer the cylinder head. Let us say at this position it may be. Now what we are doing, initially we are keeping this diathermic wall in contact with the cylinder head and the source is in contact with the diathermic wall, meaning that we are supplying the heat to the system, nothing but heat to the working fluid at constant temperature T1. Right, so how to do this one, how to achieve this one? In order to achieve this one, we need to bring the source in contact with the diathermic wall, and this diathermic wall should be in contact with the cylinder head. Okay, na? So now whenever the heat is applied to the system, what will happen? The gas, if you heat the gas, the expansion of the gas will take place, means the volume, the pressure and the temperature of the gas will increase. This will push the piston away from this one, away from the cylinder head. Means I can say that expansion of the gas, nothing but work is done by the gas. If you supply the heat, it is the work done by the gas. So during this process A to B, so we are supplying the heat. So this heat supplied is equal, that gives rise to the work done by the system. How to get the work done? So as we know, the area under PV diagram gives the work done. Therefore, if you calculated the area under the curve AB, it gives the work done during this isothermal heat addition process, nothing but isothermal expansion process. We already what we call, one second please. Hello, ఎందుకు ఫోన్ చేస్తున్నావు కటి? Right, sorry. Right, so during the, we know the work done during the isothermal process, and if you see during isothermal expansion, work is equals to P into V into ln V2 by V1, where V2 is the volume after at the end of the expansion process. V1 is the start of the expansion, volume at the start of the expansion. V2 is the volume at the end of the expansion. Okay, in that fashion I can write it is VB by VA. For A to B process, the work done is equals to PV ln VB by VA. Right, is it is clear till isothermal expansion? In order to occur this expansion process, the diathermic wall and source should be in contact with the cylinder head. During this process, heat is supplied at constant temperature. This is called isothermal expansion. During this process, the work done equal to PV. PV is nothing but I can write PAVA or PBVB, because if you draw this figure on TS diagram, if you see, A to B is isothermal. Isothermal process means constant temperature. This is A and this is B. During this process, temperature is constant. Let us assume this is the temperature T1. And B to C is the adiabatic process, nothing but isentropic process. This is B to C. During this process, entropy is constant. Again, C to D is the isothermal compression process, and D2 is the isentropic expansion process, right? So T2 is the temperature here, T1 is the temperature, right? So TAVA, nothing but PBVB, because T1 is constant, TA is equals to TB. Therefore, I can write either PAVA or PBVB. This is the work done during the isothermal process. Clear first process, isothermal expansion?
Yes, sir.
Right, next process is the adiabatic expansion, right? So adiabatic expansion, during this process, adiabatic cover is in contact with the cylinder. Now what we need to do in order to occur this adiabatic expansion process, remove the diathermic wall from the cylinder head and keep the adiabatic cover in contact with the cylinder head. If I keep the adiabatic cover in contact with the cylinder head, now it will be perfectly insulated. So whatever the heats available inside this one, right? Now this expansion will be continue, further by expense of its internal energy, right? If you see, the expansion continues adiabatically and up to the state point C. That means here the work is done by the working fluid at the expense of internal energy during the isentropic process, because isentropic process is the adiabatic process. During adiabatic process, heat supplied will be zero. Therefore, work will be done by the expense of its internal energy. The internal energy is the energy stored by the fluid, energy within this fluid, right? That energy will be utilized in order to do the work done. So whenever the internal energy is decreased, what will happen? Its temperature will be reduced. Therefore, here A to B, the temperature is T1, and the temperature from B to C, it is brought to T2, right? So because it is using its internal energy for doing the work. Okay, so it is T2, the temperature at point C. Now next process is the isothermal compression. Isothermal compression is from C to D, right? So now what we need to do for in order to occur the isothermal compression, so first we kept diathermic wall, second adiabatic wall. Now remove the adiabatic wall and keep the diathermic wall in contact with the cylinder head and connect the sink to that. Right? So what will happen during that process, right? So at C, adiabatic cover is removed and cylinder head is held in contact with the heat sink through the diathermic wall. So the piston moves inwards, means during compression process. So at the end of this, now let us say at the end of at state C, let us say this is the position of the piston. Okay, this is the A initial state, this is the A, and this is the B, and this is the C, state C, right? Now C to D, now here this is D, till C to D, what is this process? It is the isothermal compression. During this process, what will happen? Heat will be, during compression process, heat will be liberated, that heat will be added to the sink. In order to do that process, we kept diathermic wall and sink in contact with the cylinder head. So the compression continues till the state point D. So during this compression process, the working fluid releases heat to the sink and its amount is equal to work done on the working fluid during the compression, right? So we are supplying work to the fluid, thereby the heat will be liberated. That heat will be rejected to the sink at temperature T2. Okay, right. Now this is the compression process. As we know, work done is equals to PV/Ln. If it is expansion process, volume after at the end of the expansion by volume start of the expansion. If it is a compression process, volume start by volume end of the expansion, because always this ratio should be greater than 1, right? In order to satisfy that condition, for compression process, work done equal to PV/Ln, volume at the start of the compression by volume at the end of the compression. If you see here in expansion process, VB by VA, VB by VA is nothing but volume at the end of the expansion by volume at the start of the expansion. Whereas here in compression process, so volume will decrease at the end of the compression. Therefore, we need to consider volume at the start to the volume at the end. Okay, so this is the isothermal compression process. Finally, we have adiabatic compression. Once the piston reaches state D, remove the remove the diathermic wall and keep adiabatic wall in contact with the cylinder head. Now the further compression is taking place adiabatically, okay, and the right. So the compression proceeds adiabatically, and the working fluid returns to its initial state A. So work is done on the working fluid. So thereby the internal energy again increases. If you see during adiabatic expansion process, in order to do the work, what will happen? Its internal energy is utilized, and during the adiabatic compression process, so what will happen? Due to the work done on the working fluid, its internal energy is increased and its temperature is raised to again back to the T1. This is T1 and this is T2. Okay, now means you can say A to B the temperature is constant and C to D is also the temperature is constant. Okay, so here the temperature is added from source to the system, right? Now source to the working fluid, again this working fluid to the sink during this isothermal compression, right? Now we will solve the formula to calculate the efficiency of the heat engine. Okay, now so as we know from first law of thermodynamics, heat supplied equal to work done, or nothing but cyclic integral heat supplied equal to cyclic integral work done. If the system process consists of 2 to 3, means cyclic integral W means, let us say, W122 plus W223 plus W324, like that. Any process are the W421. Here I can say A to B, B to C, C to D, D to A. Similarly, Q1 A to B, Q B to C, Q C to D, again Q D to A. Okay, right. So as we know, work done equal to heat supplied minus heat rejected, right? If you see, heat is supplied during this isothermal expansion process, and heat will be rejected during the isothermal compression process. Therefore, work done is equal to, as we know, heat engine we already studied, heat supplied minus heat rejected gives the work done. So therefore W is equals to Q1 minus Q2, right? So heat supplied at which, what is the process of heat supplied? Isothermal process. So during isothermal process, it is PVLN VB by VA. P1 PV I can written as PAVA or PBVB. Again A to B the temperature is constant, so that is equals to T1 temperature. So therefore PAVA or PBVB I can written as MRT1. Okay, right. So this therefore MRT1 ln VB by VA. This is the expansion process, end of the expansion by start of the expansion volume. Similarly, now this is the Q2 is the compression process. So here we need to consider the volume before start of compression to the volume at the end of the compression. Therefore, this is Q2 equal to MRT2 ln VC by VD divided by Q1. Now, if you see, I can take MR common from numerator and denominator. Therefore, you left with 1 minus T2 by T1 into this value, log VC by, right? Now, if you see B2C and C2D, they are adiabatic process. What is the governing equation for adiabatic process? PV power gamma is equals to constant. That is adiabatic process. If you apply this process from B to C and D to A, right? If you apply between B to C, I can write. 1 second. Madam, చెప్పండి madam. Absent అయ్యింది madam. Okay, madam. Okay, madam. Okay. Now, so if you apply between the process B to C, I can say PB VB power gamma is equals to PC VC power gamma. That is one equation. Let me change the color. Right. So PB VB power gamma equal to PC VC power gamma. That is the one equation. And from this equation, I can write PB by PC is equals to VC by VB whole power gamma. Okay, and from equation of state we know PA PB VB by PB is equals to PC VC by TC. Okay, so what we need to do, I need to eliminate this pressure. Okay, so for that I can write PB by PC can be written as, from this equation, PB by PC can be written as VC by VB into TB by TC. Therefore, here PB by PC is replaced by VC by VB and TB by TC. So this is equals to VC by VB and TB by TC. If you send this VC by VB here, it will go up and it will become -1. Therefore, TB by TC is equal to VC by VB whole power gamma minus 1. Is it is clear now? Is it is clear? Just now I explained you need to use equation of state and governing law for adiabatic. So if you send this Vc by Vb this side, it will come to denominator. If you write in the numerator, you will get -1. That's what it written. Similarly, from A to B also we can write Ta by Td is equals to this one, right? Now if you substitute Vc by Vd and Vb by Va value here, again if you see Ta equal to Tb equal to T1, right now. So that is the TS diagram. Somebody unmuted, muted. A to B, B to C, C to D. This is the isothermal process. This is the adiabatic process. Now this is the temperature T1. This is the temperature T2. Means Ta equal to Tb equal to T1. Tc equal to Td equal to T2. Right? If you use this one, then yes, mute your mic. Somebody unmuted. So if you substitute here, what we will get? Tb value is T1, Tc value is T2. T1 by T2 is this much, and here also same. Ta is T1, T1 by T2 means this volume ratio is same, right? I can say that Vc by Vb is equals to Vd by Va, or I can written as Vc by Vd is equals to Vb by Va. When Vc by Vd equal to Vb by Va, this value equal to 1. Therefore, you will get efficiency equal to 1 minus T2 by T1. This is the efficiency of Carnot heat engine, right? Now here if you see this efficiency is independent of the working fluid. Yes, sir. Whatever the working fluid, it won't bother, but it depends only on the temperature of T1 and T2, means temperature of source and temperature of sink. So always, as we know, this value is less than 1, means efficiency is already less than 100%. And in order to get the 100% efficiency, T2 should be 0. When T2 is 0, then what will happen? It will interact with only one reservoir. That is the violation of second law of thermodynamics. Rather, in order to increase the efficiency, what we need to do? We need to decrease the T2, means we need to decrease the temperature at which heat is rejected to the sink, or else we can increase the temperature at which heat is supplied to the source. Okay, by increasing T1 we can increase the efficiency, by decreasing T2 also we can increase the efficiency, right? If T1 equal to T2, then what will happen? Efficiency equal to 0, right? So means whatever the heat supplied, the same heat will be rejected to the sink. In that case, the work done will be 0. When work done is 0, efficiency is also 0, right? So as I told, efficiency increases increasing in T1 or decreasing in T2. This is all about the Carnot heat engine. Any doubt? Please ask me. Very, very important.
No, sir.
No, right. Can I proceed to next?
Yes, sir.
Is this is clear, or anyone required explanation for this? How to write this? Please tell me. Temperature ratio in terms of volume ratio. Clear, no? For this, you need to use two equations. One is the governing law for adiabatic. Second one is the equation of state. I applied for B to C. Similarly, I can apply for D to A also. Right. Next, just exactly reverse of this is the Carnot heat pump. Exactly reverse of this is a Carnot heat pump. Even I can call it as a refrigerator also. Refrigerator also works on the reverse Carnot engine. Okay. Now, if you see earlier, the process is starting at A and ending at A to B, B to C, C to D, D to A. In case of heat engine, but here it is all the process would be reversed here. The adjective reverse means, so means here it is coming from A to D, D to C, C to B, and B to A. Okay. Only the process is reversed. Remaining all are same. Here now this is the adiabatic expansion, isothermal expansion. Then adiabatic compression, isothermal compression. If you see earlier, this is the isothermal expansion, this is the adiabatic expansion, and isothermal compression, adiabatic compression. Now this is reverse. Yes, 319, your mic is unmuted. 32, your mic is unmuted. 32, mute your mic. Okay. Now, so here if you see A to D, it is the adiabatic expansion process, right? So adiabatic expansion means entropy remains constant, right? So here it is during expansion process, temperature will decrease as we know. So therefore, it is a T1 temperature and this T2 temperature. Temperature is decreased from T1 to T2, and D2C, this is the isothermal expansion, and during this process the temperature remains constant. Okay, so Q2 is observed at temperature T2 from the space being cooled, right? Now during expansion process, isothermal expansion means we should maintain the temperature constant. Therefore, during this process heat will be supplied, means this heat is what we are going to supply, this heat from the space to be cooled. If you recall the working of refrigerator or heat pump, okay, now all we are taking the heat from the lower temperature body and we are rejecting heat to the higher temperature body. In order to do this process reverse, what we did, we are supplying the work for both refrigerator and heat pump. We need to add the work because here the heat is moving from flowing from lower temperature body to the higher temperature body. Okay, right. Next, C2D is the reversible adiabatic compression process. During this process the temperature rises from T2 to T1. So right, this is the T1. And finally this is isothermal compression process, during which we need to maintain the heat constant. Therefore heat will be rejected to the higher temperature body. So here we have higher temperature body. Now as usual we can see first a is the expansion process. The work done is equals to PV ln VD by VA. You can see here. One second. Sir Srikanth sir. ఎవరిది సార్? ఒకసారి వీరభద్ర అడగండి సార్ ఒక్కసారి. ఓకే, దెన్ లీవ్ ఇట్ సార్, దెన్ యూ కాంట్ డూ ఎనీథింగ్. ఓకే ఓకే సార్. సార్ అదే అదే వీరభద్రం సార్తో మాట్లాడియండి ఇంకా. ఓకే సార్. సార్ 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 దండా సార్. సార్ ఓకే, నో ఇష్యూ సార్. ఓకే సార్, నో ఇష్యూ సార్. ఓకే సార్. ఓకే సార్. ఓకే సార్, థ్యాంక్ యూ సార్. Right. So Q1 is equals to PV ln VB by VA, and as this is all just now we discussed in heat engine, VB by VA, and this is Q2. Okay, and this is also just now I proved VC by VD is equals to VB by VA, or I can say VC by VB is also equal to VD by VA, right? So heat pump COP is equal to what? COP is equals to desired effect by work done. What is my desired effect? Extracting the supplying the heat to the higher temperature body is the desired effect in case of heat pump, and extracting heat from the lower temperature body is the desired effect in case of refrigerator. In case of heat pump, supplying heat to the higher temperature body, that is Q1 is my desired effect in case of heat pump. So Q1 by work done is equal to Q1 minus Q2. If you simplify, you will get T1 by T1 minus T2. This is what I derived in starting class while discussing COP of heat pump. Similarly, for COP of refrigerator, the desired effect is the extracting the heat from the lower temperature body. This is the Q2 is the extracting heat from the lower temperature body. For that, we need to do the work, that is Q1 minus Q2 is the work supplied in order to occur this process. Therefore, Q2 by Q1 minus Q2, on substituting all those things, we will get T2 by T1 minus T2. This is the COP of the refrigerator. And we also have relation COP of pump is equals to, anyone remember? COP of pump is equals to 1 plus COP of refrigerator. 1 plus COP of refrigerator. If you add 1 to the refrigerator, so if you add 1 here, what you will get? Q1 by Q1 minus Q2. Q1 minus Q2 is the COP of the pump. Pump is equals to 1 plus refrigerator. Okay, right. Now, is it clear? Just reversing the processes in heat engine, you will get the either heat pump or refrigerator. So the working will remain the same, only the desired effect will change. Okay.
So what is full form of
COP? Coefficient of performance.
Okay, sir.
Coefficient of performance. Okay. Now we'll solve problems. Wait, let us take first problem. Can you see the screen? I pasted in Paint.
Yes, sir.
Yes, sir.
Yes, sir.
I think let me zoom. Can anyone read the question? Is it readable?
Yes, sir.
Yeah, can anyone read?
A heat engine working on Carnot cycle converts 1/5 of the heat input into work. When the temperature of the sink is reduced by 80 degrees Celsius, the efficiency gets doubled. Make calculations for the temperature of source and sink.
Okay, right. So a Carnot engine, right? So the efficiency of Carnot engine is equals to, one second. So we know efficiency is equals to, what is the formula for efficiency? T1 minus T2 by T1, right now? So that is equals to work done by heat supplied. Agree? So work done by heat supplied. This work done is nothing but heat supplied minus heat rejected by heat supplied. I can write in any way. Okay, the efficiency, right? So here given that a heat engine working on Carnot cycle converts 1/5 of heat input into the work. So 1/5 of heat input into the work, right? What does it mean? So what is work? Q1 minus Q2 is equals to 1/5 of heat input. Is this equation is clear? This is the work done. This is the heat supplied. It will convert 1/5 of heat input into the work. That is the means Q1 by 5 is equals to Q1 minus Q2. So from this I can write Q1 minus Q2 by Q1 is equals to 1 by 5. I can call it as efficiency of Carnot heat engine. Agree? Read the question carefully and understand. 1/5 of heat supplied. Heat supplied is Q1. Is converted into work done. Work done is heat supplied minus heat rejected. This is the first case, right? Now I can equate this T1 minus T2 by T1 is equals to 1 by 5. Am I audible? Hello?
Yes,
Yes,
sir.
sir.
Audible.
Right. Now second case what he did? When the temperature of the sink is reduced by 80 degrees. Now, which is the temperature of sink, T1 or T2? Tell me, which is the
T2, sir.
temperature of sink? T2, right?
T2,
Now,
sir.
when the temperature is reduced, now T2 is equals to T2 minus 80, right now? When temperature is reduced by 80, T1 minus T2 by T1 is equals to what happened to efficiency? Its efficiency got doubled, 2 into 1 by 5. Make calculations for temperature of source and sink. Now he is asking calculate T1 and T2 value, right? So from this equation, I can write T1 minus T2 is equals to 5T1. Yes or no? T1 minus T2 equal to 5T1, or I can say minus 4T1. Yes or no?
Yes, sir.
Is
Minus
this is
41
correct?
equal. Yes, sir.
5 should be multiplied here, right?
Yes,
Huh?
sir.
5 should multiply numerator. Now it will become what? 5T1 minus
Minus
5T2 is equals to T1. From this I will get 4T1 is equals to 5T2. This is equation number 1. One relation between T1 and T2. Okay. Now second relation, if you simplify this, what you will get? 2 by 5, right? So if you cross multiply 5T1 minus 5T2 plus 400 is equals to 2T1. Is it is correct? Now if you take T1 over here, 3T1 minus 5T2 plus 400 is equals to 0. From this I can write T1 is equals to 5 by 4 T2. Okay, now put T1 value here, then you will get the T2 and T1. Just go through it. Hello, sir. Sir, good afternoon. Good afternoon, sir. Where are you, sir? Okay, yes, okay, okay, sir. Come, sir. Yeah. Yes, 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 yes. Okay, okay, sir. Right. Clear this problem? Tell me any doubt in this one. Now, if you put T1 value here, you will get T2.
Sir, how you get
No,
T2 minus 80?
yeah, that's what. Here, what is given? The temperature of sink is when the temperature of sink is reduced by 80 degree. When the temperature of
Okay,
sink is
sir.
reduced by 80 means T2 is reduced by T2 minus 80. Okay,
Yes,
now?
sir, understood.
Now substituting T1 here, you will get T2 and T1. 1 into you will get these values. 1 into and simplification. Okay, now next problem. Now, can anyone read the problem? Can anyone read the problem? Is
A
it is
reversible heat engine delivers.
yes.
Yes,
Hmm.
sir.
Yes,
A
read it.
reversible heat engine
What is
delivers
it? Hmm.
0.6 kilowatts power and rejects heat energy to reservoir at 300 kilo.
Kelvin. Right
At
now,
the rate of
300 Kelvin.
24 kilojoules
Hmm.
per minute,
Hmm.
make calculation
Hmm.
for engine efficiency and the temperature of the thermal reservoir supplying heat to the engine.
Right. Now you can see here, it delivers 0.6 kilowatt power. Power is nothing but work done. Work done per time is called power only. Okay. See, work done is in joules or kilojoules, and power is in kilowatt. That's it. Okay. And rejects heat energy to a reservoir at 300 Kelvin. This is the sink to the sink rejecting, and at the rate of heat is 24 kilojoules per minute. So what is asking? Calculate the efficiency of the engine and temperature of thermal reservoirs supplying heat to the engine. What is the, he's asking? Thermal reservoir supplying heat to the engine is nothing but source. He's asking temperature T1. You can see here work done is equals to, this is what heat reject. Reject means it is Q2. So we know work done is equals to Q1 minus Q2. Work done equal to Q1 minus Q2. But here what you need to do, you should balance the units. Work is in kilojoule, kilowatt is nothing but kilojoules per second, but heat supplied is given in kilojoules per minute. So you should convert into kilojoules per second by multiplying with 60 in the denominator. So therefore kilojoules per second, because 1 minute is equals to 60 second. Right now this is Q2. Okay. Now what is the work done given? 0.6 kilowatt is equals to Q1 minus 24 by 60. From this Q1 is equals to 0.6 plus 24 by 60. If you simplify, you will get the Q1 value. Okay. So if you simplify, what you will get? 6 4 ja, 6 10 ja, 2 2, 2 5 ja, 5 is the LCM, 3 plus 2. So that is equals to 1 kilojoule per second. Q1. Q1 is equals to 1 kilojoules per second. Q2 is equals to this much. And what is asking? Efficiency. Efficiency is equals to work done T1 minus T2 divided by T1. Nothing but Q1
Sir, can you
minus
explain again,
Q2.
sir?
Sorry?
Can you
Hello?
explain from starting, sir, please?
Why?
Did not
Okay,
understand.
right. Okay, okay, right now. Is the given data is clear? Delivers power. Power is nothing but work done per second.
But how
Yes,
you
mute
get
your mic, please.
Q is equals to 24 by 60, sir?
That's what. Now, here if you see the units kilojoules per minute, 1 minute is equal to 60 seconds.
Yes, sir.
1 minute equal to 60 seconds. Therefore, I divided with 60. Therefore, this one will become, okay,
Yes, sir.
2 by
Kilojoule per
3,
second.
2 by 5 kilojoules per second. 2 by 5 kilojoules per second. Therefore, Q1 also I am getting in terms of kilojoules per second. Therefore, units are balanced. Balancing. If you are any, not only this subject, any problematic subject, if you are able to balance the units, half of the problem is over. Okay. Now, so Q1 is equals to 1 minus Q2 is equals to 2 by 5 divided by 1. So that is equals to 5 minus 2, 3 by 5 into 100. So the efficiency is equals to 60%. Okay, 520 is there. Now T1, right? He is asking T1. How to get the T1? Tell me.
Efficiency, sir.
Right, efficiency formula. Efficiency is equals to T1 minus T2 by T1. So in this one, T2 value is given. Efficiency is equals to 0.6. Yes, sir. Efficiency equal 0.6 is equals to T1 minus T2 is 300 divided by T1. So therefore, if you cross multiply, 0.6 T1 is equals to T1 minus 300. So therefore, 0.4 T1 is equals to 300. So this implies T1 is equals to 300 by 4. Sorry, 3000 by 4 it will become 4 7 28, 7500, 750, sorry, 750 Kelvin. Clear this one?
Yes, sir.
Right, with this we'll stop today. Any doubt, please ask me.
Clear, sir.
Right. 1 second, let me download the attendance.